So we are going from air into glass. Show me with your arm the normal line. Okay, perpendicular to surface. Okay, going from air to water, from a low index refraction to a high index refraction. Is it going to bend? Just think, don't say it out loud. Away or towards the normal line? Thumbs up when you have something in your brain. Tell your neighbor. Going from a low to a high, going from fast to slow, it's going to bend towards the normal line. Okay, good at that. And show me with your arm the normal line as it goes from glass back into air. Tell your neighbor what's it gonna do. Okay, here's no refraction. It's going to bend away from the normal line. Now, if this special case scenario, if this surface is parallel to this surface, then this ray is going to be parallel to this ray. It's going to bend away from the normal line. Try that a little better. It's going to bend away from the normal line. Cool with that? Ish. It's close. So, if your eyeball is right here, this object is going to appear here, shifted ever so slightly, depending on how thick the glass is and depending on your angle. So if you're looking through a window, if you're looking straight on, there's not going to be any bending and shifting. But if you're looking at an angle, that's where you're going to see this shifting of where the object is compared to where it appears to be. Okay, that's when you look at a fish tank at an angle, you get some pretty crazy stuff where you can see the fish in two different places. Oh, can't see it. Oh, there you are. That could have been problematic. Let's see if we still have a red marker. I think we're good. Maybe. Okay. Does that make sense? Like going at an angle, you can see a fish in two different spots, but you know it's not. Okay. So this is where we get these. Okay, so some pictures of some decapitations. So, okay, so this one's not apparent, but these two, you can tell that you're looking at an angle at the swimming pool. Okay, so the kid's body is actually here, we know that. Okay, but light's coming off of here, bending away from the normal line into your eyes, so you see the guy's body right here. Good with that? I didn't. I'm not that. I know. He did that on purpose. I would not have. All right. My recommendation for this one would be take it in stages. Thumbs up when you have a guess. Yeah. Great question. Perpendicular to the surface. Okay, we're going to walk through this together. Show me with your arm the direction of the normal line. Perpendicular to the surface. So, no refraction. He's doing this. So is it going to bend away or towards the normal line? Going from air to glass is going to bend towards the normal line. You okay with that? This came up last hour. I'm talking about this normal line, not this normal line. I'm talking about the normal line that's in the glass, not this normal line. It bends towards this normal line.
Wait, it just goes to whichever one is
if you were tracking before that, ignore that last thing. It goes towards this normal line. Okay? All right. Show me the normal line on this guy, on this interaction. Perpendicular to the surface. Okay. And is it going to bend? So this is no refraction. What's it going to do? Bend away or towards the normal line? Away from the normal line. Here's the normal, or like no refraction, we're going to bend away from this normal line. Correct answer was D, dangerous dinosaurs. Good with that? Okay. Now, the reason why I didn't end up doing with this, because this surface and this surface are parallel, compared to here, this surface and this surface are not parallel. Good with that? Okay. So, if you get white light, so notice how we refracted a bunch. That makes sense. We refracted and then refracted again. If we take white light and make it do this through a prism, it separates out into the color spectrum because of the different wavelengths. So the shorter the wavelength, the slower it goes, and the more it refracts, the more it bends. Okay, so it ends up bending into the color spectrum. Okay, which I'm assuming you have seen multiple times in your life through like window panes or different angled glass type things, or like crystal chandelier type decorations, or you've seen a rainbow on the wall, or you've seen, looking at glass, you've seen different colors, and then you move your head and then it changes the color. Okay. Dispersion. So what is dispersion? When white light is separated into the color spectrum due to refraction. When does it occur? When white light is refracted a lot. Okay. Dispersion is when white light is separated into color spectrum due to refraction, and when white light is refracted a lot of refraction. There? All right.
What about like the speed of the light?
Yep. Yep. Sure can. So, which color has the least angle of refraction? This is red. Has a long wavelength. Ugh, that crashed and burned. And then which one has the greatest? It is blue. Sorry, purple. Not blue, so like goose. Purple. Try to do something a little tricky here. And it has short wavelength. Therefore, have you ever seen this in chemistry? Therefore, this 3 triangle dots. Therefore, goes slower and bends more. Short wavelength, therefore, goes slower and bends more. Through that. Did that answer your question? Okay, so when do we find this dispersion effect happening in nature? Rainbows. Okay, so let's talk. So I'm assuming you've lived life enough to like know like when the conditions are ripe for a rainbow. Rain, the sun comes out, like, ooh, rainbow. It's got to be somewhere. Start looking. Okay? So here's how this works. You need sunlight, you need raindrops, and you need your eyeballs. Okay. So the white light comes in and it refracts once, going from air into water, bends a little bit. Okay. Remember in the fish tank how some of the light refracts and gets out, and some of it reflects back. Okay. So most light gets out, but some of the light is reflected back in. And then when it refracts again, this is enough to cause dispersion. Separates out. Okay. If you look at this is a laser going through like a water droplet, doing this, most of it gets out, but some of it's reflected back. This is the portion of light that's due to a rainbow. Notice that it's not very bright. This is why we don't see a rainbow all the time. And there needs to be a lot of sunlight in order for us to perceive this, to see that. You okay with that? Okay. So it turns out that every raindrop is spitting out a rainbow. Every one. Okay. And if you've seen a rainbow, what color is on top? Red. And on bottom? Purple. That is a great question. Why is it opposite? So, check this out. So, rain's falling, sunlight goes through. Each raindrop's kind of spitting out a whole color spectrum. But red from this one is shooting into your eye. So you see red here. Purple is shooting over your head. You don't see that. A lower raindrop is shooting purple into your eye. Red is hitting your chest from that raindrop. So you see the color spectrum: red, orange, yellow, green, blue, purple. Good with that? Does that make sense?
Is there a way to calculate the amount of deviation given wavelength has?
Yes. Yes. Yep. We're not going to talk about it, but yes. Okay. Hang on to that. That's a great question. We will get coming up in like 5 slides. Okay. So the raindrops here at this level are shooting red into your eye. The raindrops here are shooting purple into your eye. Okay. Joseph.
How do rainbows show up? Like usually they happen after it stops raining. So how do rainbows?
Yes. Beautiful question.
So many good.
Where is the rainbow? Whoa!
Okay. So
It's like you can see the future. Oh, that question? Next slide.
been teaching this class a long time. I know.
Are you from the future?
It's like time travel. Oh, that's APD.
Okay. So in order to so it stops raining, the sun comes out, you're like, rainbow, it's got to be somewhere. Where should I look? Where should I look? You should look so that the sunlight's coming here. You should look away from the sun. So here's you. So you're like, where's the rainbow? The sun's over there. Go, boom. There's the rainbow. Always put your back to the sun. Good with that? Okay. So now you can hunt for rainbows more effectively. You don't have to be sitting there, oh, Like, sun, boom. All right. Next question. Correct answer is B. If you put your back to the sun at high noon, that's like doing this. That makes sense? Okay, so it's going to happen when the sun's at the horizons. Okay, the lower the sun is to the horizon, the higher the rainbow is going to be in the sky. Okay, at noon you can get a rainbow, but it's not going to be from rain. It could be from your hose, your sprinkler system, or something where you can look down as you spray your hose and see a rainbow where the sun is at your back. That makes sense? Okay. Okay. So
That's on the good side.
So as you take a step closer, you are now here. Raindrops that were shooting purple into your eye are now shooting red into your eye. And now raindrops that are lower are now shooting purple. So as you move closer, what's happening to the rainbow? It's moving with you. So the leprechauns are like, go ahead, kids, try it. Not gonna happen. It's moving away. As you take a step closer, it's taking a step further away. It's always the same. It's always this angle. So the leprechauns have another trick up their sleeve. Ready for this?
What? You can come
They
up.
fly.
They're actually complete circles. The Earth just gets in the way, and like end of the rainbow. It's a circle. Okay, and so it's really a complete circle, but the Earth gets in the way. Okay, if you can see, so these are like skydivers being able to like see, like it's raining below them. You can see that when you use a hose or sprinkler at noon, and you get a full, like you do one of those nozzles, Mr. Nozzles. You can get a whole circle except for your shadow, where your shadow is. Try it. Okay. Good at that. Okay. So, double rainbows. So this is how a primary rainbow bounces around. The light bounces through a raindrop. Secondary rainbow light does this. It reflects twice in there. So the intensity of this light is super faint. It happens, but it's not. It's so faint that we don't see it unless the sunlight is super bright. Then you can see a double rainbow. That's why they're rare. Okay, check this out. See this order? Look at the order of the rainbow of the secondary.
It's opposite.
Crazy.
It's like a reflection.
Cool with that? So next time you see a double rainbow, you like look at the color order. Cool with that? Now, sometimes you're able to see rainbows in the winter or the fall time when it's cold, and it turns out to be close. You're looking near the sun, like it's around the sun. It's not putting your back to the sun. You're actually looking in the general direction of the sun, and you see like smeared rainbows in the clouds. This is due to refraction. It is not a rainbow. It's due to the ice crystals in the upper atmosphere. I've seen stuff like this here in Indiana. I've never seen anything like this, but known as sun dogs. Okay. All right. Have you? Well, nothing. Have you ever looked over a hot road, a hot roof, like a parking lot, open the car door on a hot sunny day, open the oven after cooking, and seen heat waves? Does everybody know what I'm talking about? Okay. This is due to refraction. Light travels faster through hot air because it's less dense. And compared to the cooler air, it causes light to bend. That's why you get the wavy appearance. It's bending light. Okay. So these are pretty extreme examples, or looking at the exhaust of jets. But that heat wave ripple stuff, that's totally a refraction phenomena. Good with that? Someone asked, I don't know if it was this hour, remember I was showing the bomb videos and the explosions, and you could see the shockwave bubble? That's because it changed the density of the air. Made it super dense. It was super compressed, so it was bending light. That's how we were able to see it. Cool with that? Okay. So, have you ever been driving on a hot sunny day and seen water on the road in the distance? You're like, wow, it must be raining up there. And then you get up there and it's gone. You're like, wow, it must be so hot it evaporated super fast. So what you observed was a mirage. Okay. And here's how it works. So quick little disclaimer. This picture has been like truncated, like shrunk. It should be like the dude's like really far out there. Okay. So the temperature near the surface of the road or wherever is super hot. Okay. And it cools down as you go away from it. It's being baked right here by the asphalt or whatever, the roof. Okay. Light that would have hit here is going through different temperatures of air and is getting faster and faster because it's getting hotter and hotter. And so it's bending away from the normal and away from the normal. At some point, it experiences total internal reflection and bends back up to here. You think you see, because light should have been here, but you think you see a palm tree here because light is bending into your eye from the palm tree. You think you see it right there, and it behaves just like as if water was sitting right here and reflecting light, boom, boom, and it looks like water. Okay, so what you're seeing is the light from the sky coming here and being bent up into your eyes. And so you see an image of the sky and the vehicles. This pretty typical Indiana, hazy, muggy. Okay, so here, this picture isn't the greatest, but I liked it because you can see the image of the headlamp. So light would have hit here on the road, but it's being bent up into your eye, and you see an image of the headlight right there. Cool with that? So you see why in the desert, if you're really thirsty, this could look really like, yes, oh. That makes sense? Yeah, you could. Okay. All right. So this happens in reverse as well. So near the Arctic Circle, like in Scandinavian countries, the cold water makes the air cold, and up above that there is warmer air, and so light, instead of being bent up, is bent down, and so you see an image upside down in the air. So this is an image of the ship. Okay, this is the distant land. Light that would have gone over here is being bent down, so you're able to see that. Pretty crazy, huh? Okay. All right. We are going to do a fun activity.